Okay. Okay, so this will be our last lecture, online live. Okay, towards the end of the class, I will give you the assignment that you have to do. So today we are going to do the exercise for the last chapter. Okay, present. Okay, so the last chapter is about rockets. So it's a bit different than the previous 4 chapter, which is mainly about air breathing engine, right? Turbofan, turbojet, and the components within the turbofan, turbojet engine, which is compressor, combustion chamber, turbine, etc. Nozzle. Okay. So this time, just this chapter, we are going to look on the rockets, okay, the non-air breathing engine part. Okay, I think I'm sure some of the content, some of the parts we have learned a bit in maybe space mechanic, okay, the rocket equation, etc. You learn more details in space mechanics course, okay. And this particular chapter also will be continue, inshallah, in the next course, which is Space Launch Technology, EAS 3514. So propulsion will be the prerequisite for the Space Launch Technology course. So you have to pass this course, okay? So because for Space Launch Technology, okay, it's mainly about space propulsion, okay. So here in this general propulsion course, I just introduced to you a bit about the principles of the operation of the rocket engine and some of the performance parameters, of course, performance parameters of the rocket. Yeah, okay. So the details more you will learn more in next year, inshallah. Okay. Okay, so I have 3 exercises. Maybe we do 2. Okay, here in the slides I have 3 exercises, but I think we will do only 2 together. And if you have enough time, I try to do. We will try to do the last tutorial on the turbo machinery that we have left the exercise for, right? About the axial turbine. If we have enough time, we can see that tutorial as well, okay? Because I think for the rocket tutorials, exercise is not too complicated. It's just that you have to know which parameters, which value to put on which values, okay? Okay, so for the first one, okay? So the first one, a rocket projectile has the following characteristics. Initial mass of 200 kilograms. So when we say initial mass of the rocket means the whole rocket body, including the propellant, the mass of the propellant, the system, etc. Okay, the whole mass, the initial mass is 200 kilogram. Okay, and then mass after rocket operation means after launching, the rocket, the whole body of the rocket reduced to 130 kilogram. It's logic, okay? Because for a rocket body carries mass of the propellant, liquid propellant, solid propellant, right? Okay, so after launching, obviously this propellant will be burned, okay, combustion, okay, in the combustion chamber. So the total mass of the rocket body will be reduced. Okay, so the after launching, the final mass it is reduced to 130 kilogram. Okay, because we have lost the mass of the propellant. Okay, and then the payload, non-propulsive structure, etc. Okay, this is the mass of the rest of the system, the payload. Okay, not including the propellant mass, which is 110 kilogram. Okay, and then the rocket operating duration around 3 seconds. So it's just a small rocket, okay, 3 seconds. And then average specific impulse of propellant. So remember, in the, okay, okay. before this, I have introduced to you about this parameter specific impulse for everyday engine, right? For turbofan turbojet, but we didn't really use apply the specific impulse in our calculation, because for everyday engine, turbofan turbojet, etc., it is more in order to evaluate those performance. We normally calculate the thrust, the propulsive efficiency, right? Okay, but for a rocket engine, it is more interesting. It is more important to know the specific impulse, the effective exhaust velocity. Okay, rather than thrust force or propulsive efficiency like the everyday engine. Okay, we still have those equation, thrust, force, etc. for rocket, but it is more important to know the specific impulse, the exhaust, the effective velocity, because for a rocket we want to know how long it can endure, how long it can last. Okay, so that's why the calculation of specific impulse 240 seconds is more important. Okay. Okay. Okay, so next, okay, so determine the vehicle's mass ratio, propeller's mass fraction, flow rate, thrust to weight ratio, etc. Okay, even though there is a lot of parameters to calculate, but it's just simple. It's just that you have to know which value to put on the calculation. Okay, so first one, initial mass. Okay. Mana tadi? Wait, okay. So initial mass ratio, we want to calculate okay, the vehicle's mass ratio, the rocket mass ratio. Okay, so we write it as MR. Okay, mass ratio. So the vehicle's mass ratio is the ratio of the final ratio, the final mass over the initial mass. Okay, final mass over the initial mass. Do we have it in? I'm looking back on this lecture slides. Did I give you this? I think I give you a ratio. Specific impulse. V rocket. Okay. Mass ratio. Yeah, yeah. For any mass ratio is for any burn. For any burn means for any propeller mass burn, the ratio between the rocket's initial mass and its final mass. Okay. This okay. Okay. I'm just checking the lecture slide. Okay. So okay. The mass ratio. So the mass ratio. The final mass is 130 over the initial body 200. Okay. So just 130 divided by 200, so you get 0.65, the mass ratio. Okay. And then what else? Propellant mass fraction. Propellant mass fraction. So the propellant, the solid propellant or the liquid propellant. Okay. Propellant mass fraction. So the for the propellant mass fraction, you okay, we have to in order to calculate the fraction, which the ratio, we have to eliminate the payload, the non-propulsive structure, etc. Okay, the rest of the system. Okay, so what we have sekejap ni. Okay. So tunjuk MF. Oh ini this one MF over got to eliminate the 110. Okay, the payload payload structure. Okay, this one also. Okay, sorry, this calculation is not finished. 130 minus 110, and also below 200 minus 110. Okay. So we have 0.22. Okay, 0.22. Okay. Okay, minus the payload here. Okay. Okay, next, the propellant mass fraction. So for the propellant mass fraction, we use the notation, this notation, or whatever in the notation. Okay, so for the propellant, we MO, the initial the body of the mass, the body of the rocket. Okay. Okay, initial mass of the propulsive system over minus the final mass. Okay, and over the initial. Okay, so propellant mass fraction, the mass fraction of the propellant. Okay, the initial mass, which is now we know that the initial mass, we have to cut out the mass of the payload. So the initial mass will be 90. 200 minus 110, 90. The initial mass, cut out the payload, non-structural, non-destructive, etc. And minus the final 130 minus 110. So we have 20 over 90 again. Okay, the final mass of the rocket. Okay, by eliminating those the non-propulsive structure. Okay, so propellant mass fraction is this one, 90 minus 20, so 70, because we already after final already the mass of the propellant is the difference between the initial mass and the final mass. Okay, because obviously we will burn all those propellant while launching. Okay, so 90 minus 20 over 90, again 0.778. Okay, so this is propellant mass fraction, the fraction of the mass of the propellant, liquid propellant, also the propellant inside which we burn, okay, while launching. Okay, so this initial minus final, so the propellant. Okay, 0.778. And then propellant flow rate. Okay, flow rate, we just so the propellant just now is 70, 90 minus 20, or 200 minus 130 also can. So the difference is 70. The propellant mass is 70 kilogram, and the duration of the rocket given is 3 seconds. Okay, so 70 divide by 3 seconds, so you have the propellant mass flow rate. Okay, so it's very simple. Propellant mass flow rate, we write as m dot. Okay, mass flow rate of the propellant, so we have 70 over 3 seconds, so it is 23.3 kilogram per second. Okay, next, propellant flow rate, thrust. Okay, since it is given here the specific impulse, okay, the value of the specific impulse, so we can use that value to calculate the thrust. Okay, in the lecture slide, which equation that I give you, I give m dot ve, but we don't have exhaust velocity here. Effective exhaust velocity. Okay, okay. So we can use other equation to calculate the thrust. So here we use the specific impulse. Okay, so specific impulse is in seconds. Okay, is in seconds. force, thrust is a force. So force in Newton is kilogram meter per second square, right? F equals to ma, right? Kilogram meter per second square. So here we have only seconds, specific impulse in seconds. So we need another parameter which can complete, okay, the calculation of the thrust force. So what are we going to use? Okay, so imagine here, because this equation is not given in the slides, lecture notes, but that's why we have to think, in order to calculate thrust force. You just check on the unit. So this one is kilogram meter per second square, right? This is second. So we need something that has kilogram and meter per seconds, right? Okay, so we have calculate this one, the mass flow rate. So obviously we have to use the mass flow rate values. Okay, so mass flow rate, right here, mass flow rate. So now kilogram second. So we need the acceleration, okay? Because a specific impulse is in seconds and mass flow rate is in kilogram per second. So you are left back with kilogram. So we need this acceleration meter per second square values. So obviously for a rocket, what is the acceleration? The acceleration, the parameter for acceleration is the gravity acceleration. So G. Okay, so in other words, this is the weight of the propellant, m.g. Okay, so we just calculate this one. So specific impulse is 240 multiplied with 33.3 and 9.81 gravity acceleration. So you have around 54.8 not point, okay, 54,000 ataupun kilonewton, okay, 54,085 I use kilonewton lah, cantik sikit, okay, kilonewton, okay, 54.85 kilonewton. Okay, so that is for thrust force of the rocket. And then thrust to weight ratio, okay, the thrust to weight ratio. So we have the value of the thrust, and now we want to calculate the weight ratio, okay. So the weight will be, just now, okay, the weight of the body, the initial mass, the initial, for initial value, we have F over what we want to write, m dot m dot g. Okay. So this one 54.85 kilonewton, or change it into Newton. And this one is 200, the initial mass of the rocket, times 9.81. Okay, so we have around 28. Okay, 27, 28, something like that. For the ratio, thrust to weight ratio. Means that for each kilogram of the weight, kilogram of the weight of the rocket body, for 1 kilogram rocket body, it can produce 28 Newton of force. Okay, so that's what it means by thrust to weight ratio. Okay, so we obviously we want to achieve high value of this thrust to weight ratio as possible, so that with a limited or minimum weight of the body rocket, we can produce high thrust. Okay, more thrust. So the higher this value, the better. Okay. And thrust to weight ratio for final. So for this is for initial body 200, for final 130. So just the same calculation, 54 kilonewton divided by 130, the final mass, times the gravity acceleration 9.81. So you have around 43. 43. Okay, because Newton and Newton, so there's no unit. So 43 for the final thrust to weight ratio. Okay, so the final, of course, because of the speed, the velocity is at high speed, is more bigger. Okay, after launching. So that's why one of the important criteria, the thrust increase at the final value. Okay. Next, acceleration of vehicle. Okay, acceleration of vehicle. Okay, so actually dia just calculate back. Just want to know the acceleration of the vehicles. Acceleration of the vehicle. So we have the final. We take the final because after launching, right? Okay, the effective exhaust velocity. So acceleration, maximum acceleration, maximum A is 43. Okay, 43 times the thrust to weight ratio times the again G. The gravity. Okay, so you have the maximum acceleration. This is no unit because this is a ratio, and this is the meter per second square. So you have around 4 to 1 meter second square. Okay, and then actually this value is not very important. More important is the effective exhaust velocity. Effective exhaust velocity. Okay, means like it's kind of like final velocity, but we don't call it as final velocity because it's more important to know the effective of the velocity exactly actual of the rocket after launching. So we pronounce it as effective exhaust velocity. Okay, so this effective exhaust velocity, we use the specific impulse. Okay, specific impulse times the gravity. Okay. Specific impulse, effective exhaust velocity, specific impulse with the G. So you have 240 times 981, around 2000, 52 meter per second. Okay. Lagi dua lagi value. Total impulse. Total impulse. Force time this time. 54 jangan 16. 54 times 2, 3 around. Okay, there are two methods to calculate the total impulse. One method by using all the values that we have here. Okay, total impulse by using the specific impulse times the the 70 is the mass of the propellant. The mass of the propellant just now M dot M dot mass of the propellant 70 and G. Okay. So this one 240 times 70, the mass of the propellant, and 9.81, we get around 164,000 or 164 kilonewton per second. Otherwise, we can also calculate by using the formula given in the lecture slides as total impulse is the force times the time, okay, duration, because we have this value as well. So force just now 54.85 kilonewton times the duration 3 seconds, so we get around 162 kan, 163 kan. So it's still more or less the same, 164, 163, okay. So either one you can use. And then last one for this exercise, impulse to weight ratio. Okay, impulse to weight ratio. So you have the impulse 164 kilonewton and divide by the weight ratio. Weight ratio 200 minus the 110. Okay, the initial weight ratio. Okay. Impulse to weight ratio. Impulse to weight ratio. 164,000 divide by just now the weight, the initial weight minus the okay, minus the all the non-propulsive the 110 non-propulsive payload, etc. So 200 minus all this. So 200 minus 110, 90 kilogram is the real weight of the rocket, including the mass of the propellant times G. Okay. So this one you have 185.75 second. Okay. Okay. So that's it for exercise 1. So basically the calculation is not complicated. Just calculate all the performance value. The most important values I would say is the effective exhaust velocity, the impulse, total impulse, okay, and the propellant mass. Yeah. So because you want to know how much the propellant is used throughout the rocket launching. Okay. Okay, everyone. Any questions for exercise 1? Oh, ada lagi nak masuk tu pasal. Exercise 1 okay?
Doktor nak tanya. Untuk thrust to weight ratio tu memang kena check initial dengan final lah. Thrust to weight ratio.
Impulse to weight ratio, ya?
Thrust to weight ratio. Thrust.
Yang kan? Thrust to weight ratio, okay?
Yang kena cari initial dengan final lah.
Ya, dia tak sebut personally kan kat sini kan. Ya, saya cari. Boleh je yang penting is the final kan. Sebab lepas tu kita nak guna untuk calculate the effective velocity tu kan.
Okay.
Tapi bolehlah calculate initial dengan final. Otherwise mention lah.
Okay, doktor.
Okay. Okay, we proceed to exercise number 2. Ada yang baru masuk ni. Yang baru masuk, those who just enter, later on you catch up lah. Okay, okay, exercise number 2. Ada yang sama, okay. This is the mass. Okay. Okay. Kejap. Okay. Okay. So we do the number 2. Two. Okay. Okay. So first one. So we have this problem. The following measurements for at sea level for solid propeller rocket. So we have those parameters. So first is M is the mass of the rocket body. So initial minus the final. Okay, determine the mass of the rocket. So M is the initial minus MF. Okay, sekejap bising. Okay, the mass of the rocket, initial minus final. So you have initial minus final, 1,210 minus 215. For those of you we just enter, we have already proceed on exercise 2, second exercise. Okay. So some of the parameters I've already explained with previous just now. Okay, so 1,210 minus 215, the initial mass minus the mass of the final of the rocket after the test, after launching. So okay, one DDD. So let's 95, 195 kilogram. Okay, and then we want to calculate the mass flow rate. So the duration of the burn duration is the duration, we suppose it is the duration of the rocket. Okay, so m dot over the time, mass over the time. So m dot is mass over time is 1195 divided by 40 seconds. So you have around 24.9 kilogram per second. The mass flow rate of the rocket. Okay. Next, the nozzle area. Okay, because in order to calculate with next values, the V2, the effective exhaust velocity, specific impulse, etc., we need to calculate first the nozzle area given here. Okay. So the nozzle area for at the throat, because we are given with the diameter here. So nozzle area at the throat, we call it AP, pi d square over 4. So this diameter is 0.0855. Okay, 0.0855. Another one at the exit. So this is at the throat, at the exit. With diameter 0.27. Okay, 0.27. So you have the area around 0.00574 meters square, this one 0.574. Kurang satu, just minus 1, 0. Okay, so this is the area. Okay, next we need to calculate the final, okay, the average exhaust velocity. Okay, it is like I've mentioned just now, is a bit different than the effective exhaust velocity. Okay, so we calculate first the average exhaust velocity, which is by using, okay, the thrust equation, because we have thrust and we have this area. And we have pressure, the value of the pressure. So like the normal thrust equation for every engine. So VE F over M dot just now, the mass flow rate, and then minus P, what we want to call it, P at the exit, the 0.05, 07, P exit minus the P ambient, P exit minus the P ambient, times A, the area, divide also by the mass flow rate. Okay? Okay. So normally we have this mass flow rate here on the left hand side. Okay? But now, since we want to calculate only the velocity, so we divide those force, this force, the thrust force and the pressure force by the mass flow rate. Okay? So force is 62 just now, 62,000, and this one is 34.9 calculated earlier. P exit is 0.07 megapascal, and ambient you can use 1.013, the atmosphere, but 1.013 is in bar, so if you change it into megapascal, so it should be 0.1013, okay? And divide by, multiply with the area calculated just now, the exit area, over the mass flow rate. So we have the average exhaust velocity around 2,500 meter per second. Okay, so by using the the normal thrust force equation, I said that we divide all those force, the thrust force and the pressure force, by the mass flow rate, because when we just want the velocity. Okay, next is the C. C here is the effective exhaust velocity. Okay, so effective exhaust velocity, we use the specific impulse. Okay, so we calculate first the specific impulse. The specific impulse is the F over mg, like just now. Okay, m dot g. So the thrust force is 62 again, 62,250 over the mass flow rate 34.9 again, times the acceleration 9.81. Okay, so we have specific FP. Okay, so we have the specific impulse in seconds, 255 seconds. Okay, 255 seconds. so effective exhaust velocity, VE, otherwise we could confuse, UC, okay. So I, the specific impulse, multiply with G, the acceleration. So 2255 times 9.81, which is around 2,500 kan, 25 10, 2,500 meter per second. Okay. Okay. Okay, last one. The effective velocity and the specific impulse at 1,000 and 25,000 meter altitude. Okay. Okay, so we need to know first the ambient pressure at 1,000 and 25,000, because just now 1 atmosphere is the pressure, ambient pressure at sea level. For 1,000 at 1,000 altitude, we have P ambient given around 0.0898 megapascal, and at 25,000 meter altitude, the P ambient is 0.00255, 0.00, so smaller, 255. Okay, the higher the altitude, the lower the ambient pressure. Okay, so we want to calculate the effective velocity. So at different altitude than the sea level, because we already have the average velocity just now, the VE. Okay, so at different altitude, we just to include the thrust, the pressure force. Okay, the velocity of the pressure force, the second part just now of the thrust force equation. Okay, so this one, C, for example, C. Okay, the average velocity calculated just now, 2,572 meters per second just now, plus, okay, because we have to take into consideration the different ambient pressure at different altitude. Okay, so this one, P exit is still the same, okay, which is 0.07 Pascal just now. P exit minus P ambient, so P ambient depends on the altitude, okay, and the area also the same, area still the same, and divide by the mass flow rate, okay, the 24.9 mass flow rate of the propellant, okay. So this is in meter per second velocity unit, okay. So this one no need to divide by m because we already have velocity. Okay, so for 1,000 meter, at 1,000 meter, 1,000, so V2 just now 2,572, the average velocity, average exhaust velocity. So this one, PE is the same, 0.07 megapascal, divided by the ambient, 0.0898. Okay, so the ambient is higher than the the exit pressure, okay, divide by this one is tadi 0.0574, okay, the exit velocity divided by 34.9. Okay, so the effective velocity is around still around 2,500, okay, 2527. Tak lari dari sini, okay. So this is effective velocity at 1,000, and just to include the specific impulse. So the specific impulse is the effective velocity divided by g. So you have around 2 seconds. 258 seconds. Just now at sea level we have 255 seconds. So this is 258. So just a small, slightly different. Okay. Means that the duration that the rocket can last, okay, with the velocity 2,500, etc. Okay, next is the so the same calculation, just give the answer. Okay, the same calculation for for altitude 25,000 with ambient pressure 0.00255. So we have C, same method. So we have C at 25,000. C 25,000 is around, after calculation, 2,700 meter per second, and I SP at 25,000. This time it's a bit different to 278 seconds. Okay, 278 seconds. Okay. So assume an invariant thrust. Okay, so we assume constant thrust just now, ideal case, and mass flow rate and negligible short start and stop ratio. Okay. Okay, so we throughout the launch of the rocket, we use the same value of thrust 62,000 and the mass flow rate 24.9 calculated just now. Okay. So that's it for exercise 2. Okay, everyone. For those who have just entered when I've just begun the exercise 2, you have to look back exercise 1. It's very simple calculation, just that you have to know the definition all of those parameters. What is effective exhaust velocity, what is total impulse, what is specific impulse, thrust to weight ratio, etc. Okay. Okay, so there's one exercise left that you can do by yourself. Okay. The following data, we have thrust force, propellant consumption, means the mass flow rate of the propellant, okay, velocity of the vehicles, the average velocity, and then we have the energy content, okay, because we need to calculate efficiency this time. Okay, so the equation for efficiency is given in the lecture slides, okay. Otherwise, the definition is the same, okay. The initial energy given to the vehicles and over the power output, okay, the energy produced by the vehicle rocket, okay. Okay, so this one you can do by yourself. Now I want to finish the exercise about the turbine, the AC turbine that we have left last 2 weeks. Which one? Okay, this one. So we go back to the previous chapter about the turbine. Okay, this one last exercise. Sekejap, So a single stage axial flow gas turbine has a mean radius of 30 centimeter and a blade height at the stator inlet of 6 centimeter. Okay. The hot gas enter the turbine stage at 1900 kilopascal and 1200 Kelvin. So the turbine inlet temperature and the pressure, the turbine pressure, inlet pressure. And the absolute velocity leaving the stator, C2. Okay, remember for turbine, the moving part is the rotor. Okay, so the position of the turbine, we have nozzle or stator, rotor, stator, rotor, stator, rotor. Okay, so that's why when we position the location, okay, of in the turbine, 1, 2, 3 exit inlet. So number one, our location number one is that is at the stator inlet. Okay, number two is at stator outlet or the rotor inlet, and then number three is rotor outlet. Okay, so that's why for turbine we focus more on the position 2 and 3 because 2 and 3 is the inlet and outlet of the rotor. It is the rotor which is moving. Okay. Meanwhile, for compressor, okay, we focus the position is rotor, stator, rotor, stator, rotor, stator. So depends on how many stage we have. So we focus more on the position 1 and 2 because it starts with rotor. Okay, so rotor inlet, rotor outlet for compressor is position 1 and 2. So that's why for velocity triangle of a compressor, we sketch, okay, we focus on the position V1, V2, W1, W2, C1, C2. But for turbine, C2, C3, V2, V3, W3, W2, W3 and those angles. Okay, because it is the rotor which is the moving part. To calculate the velocity, to calculate the energy, okay? Okay, so the absolute velocity, that's why given here at C2, leaving the stator, inlet rotor. Absolute velocity leaving the stator is 600 meter per second and inclined at an angle 65 degree to the axial direction. So to the axial direction, and incline is the alpha 2. Okay, means it is a bit inclined. It is not directly horizontally. Okay, so if the fluid enter horizontally, so the alpha will be 0, no angle. Okay, but here it is said to be inclined at an angle 65 degrees. So this is alpha 2. 2 because of the position, leaving the rotor inlet, alpha because the acceleration. Okay. The relative angles at the inlet and outlet of the rotor blade are 25 degree and 60 degree. So when we say relative, relative is the related with the relative velocity, W, relative velocity. So relative angles are beta, those beta. Beta 2, inlet rotor, beta 2, outlet rotor, beta 3. So beta 2, 25 degree, beta 3, 60 degree. Okay, because relative angle is beta, related with relative velocity W. Okay, kalau if alpha, it is related with the absolute velocity. Okay, C. Okay, now, okay, the stage efficiency is 0.88. Okay, now calculate the absolute angle alpha 3. Okay, So by using the tangent, okay, those velocity triangle, so we can calculate first the absolute angles because we already have alpha 2, beta 3, so we can use whichever uh, equation. So we focus on the tangent alpha 3. So we use this one. If you want to look back on your velocity triangle that we have sketched for exercise 3, okay, we can use the same velocity triangle. So we have tangent alpha 3 is tangent beta 3 minus tangent alpha 2 plus tangent beta 2. Tangent beta 3 minus tangent alpha 2 plus tangent beta 2. Okay. In your exam, you can search before the exam. You can search. You can derive the equation of this tangent velocity triangle before the exam, so that you save time. You already have all this because it is open book. So if you already have all those velocity triangles formula, so you don't need to re-derive back during the exam, so you save time. Just faster. Okay. Otherwise, you can always search back the velocity triangle. Okay. So we use this calculation because we have all those the values of the angles. Okay, otherwise we use we have to look back on the velocity triangle and see which velocity do we have, and okay, do the Pythagoras. Okay, now we have all these angles, so we just use the angles. So this one tangent. Okay, so we have alpha 3 equals to around 3 degree, 3.08 degree. So it's just very, very small angles of the fluid leaving the alpha 3, leaving the rotor. Okay, so it is nearly totally horizontal. Okay, around just 3 degree. Okay, next, the rotor rotational speed in RPM. So rotor rotational speed related with U, okay, the value U, and then we need to change into RPM. Okay, but first we can calculate U first. So U, since we have C2 given and we have alpha, so we have this equation U, CA. There's a lot of definition for U. So I just use this one, alpha 2 minus tangent beta 2. Okay, I avoid using alpha 3. You can also use the equation that involves alpha 3, because if in case we have wrongly calculated alpha 3, it won't affect your calculation for U. Okay, so just choose wisely which value you want to use. Okay, so I choose this one, alpha 2 and beta 2. Okay, so alpha 2, beta 2 given, we need to calculate CA, the axial direction, the axial direction of the absolute velocity C. So CA, if by looking at the triangle, velocity triangle, CA is the C2 times cosinus alpha 2. Okay, because it's just beside. Okay, cosinus alpha 2. So CA is around 253 meter per second. Okay, so we have CA, C2 cosinus alpha 2 equal to 253 meter per second. So U Just include all those values, 253, tangent alpha 2, tangent beta 2. So you have U around 425. 425 meter per second. Then change it into rotational per minute. So we write it as N, rotational per minute. Means that you have to U, the velocity, multiply with the diameter. So it's given here the radius, so you can calculate with the diameter. And divide by pi, 3.142, and the minute, okay, second. This is second, so change into minute. Second change into minute, so multiply with 60 seconds. So N, you get, besar, 13, 135456 rotational per minute. 54576 because it is in rotational per minute. Okay, RPM. Okay. Just a minute. Okay, you can verify back the calculation. So U is actually pi n d over 60 seconds, pi n d. So just calculate back. U multiplies with 60, divide by pi and diameter. Okay. So rotational speed in RPM U, N. Okay, next is the stage pressure ratio. Stage pressure ratio. Stage pressure ratio means pressure ratio P1, the total pressure ratio inlet over the outlet, because turbine is the opposite of the compressor, so inlet over outlet. So we want to know the ratio of the pressure. So we need to calculate the pressure ratio. Here we can use, since we don't have the pressure ratio directly, we don't have the value of the pressure. We want to use those values of tangent that we have. Okay, so first we have beta 2, we have beta 3, 35 degree and 60 degree. Okay. We use this 253. Okay, we use the definition of temperature stage. Okay, because we want to calculate the pressure stage. So we use the temperature stage, the difference of the temperature stage. So this is UCA. Okay, there's a formula for this, UCA over CP, the specific heat, and tangent. Here we use tangent alpha 2 plus tangent beta 2. Okay, for stage pressure ratio. Stage pressure ratio, UCA over CP, tangent alpha 2 plus tangent beta 2. So U, 425 just now, 425, CA is just now 253. Okay, CP around 1,100. Six is given here, 1168. But we can also calculate this one by using gamma R, etc. Okay, and then tangent alpha 2, 65 degree plus tangent beta 2, inlet rotor 25 degree. So we have the stage pressure ratio. Okay, the stage pressure ratio around 202, 203 Kelvin. Okay, means that the ratio of the pressure ratio, temperature, inlet and outlet temperature of the stage of the turbine 203. Sekejap Okay, ini tadi slides. And then the stage pressure ratio P.1 over P total 3. Okay. So since we have the temperature, so we use the isentropic, okay, definition between the pressure and temperature. Okay, and because we have the efficiency, okay, the stage efficiency 0.88. Okay, it means the efficiency of the turbine. So we use that definition, the turbine efficiency, which relates the pressure and temperature. So we have 1 over, this one you have to look back in your thermodynamic, okay, 1 minus delta T stage over the efficiency 0.88 times the initial temperature, which is given 1200 Kelvin. Okay, so all this gamma minus 1. Okay, so this comes from the relation of the efficiency of the turbine efficiency and the between pressure and temperature isentropic relation. So you have this one. So finally, the pi stage is around 2.35. Okay, the stage pressure ratio means that the initial pressure, the initial total pressure is around 2.3 higher than the final pressure. Oops. Ada nak mas? Sekejap to admin staff, tak apalah. Okay. Macam mana dia staff ku. Okay, so ada meeting. Kejap. Okay, okay, flow coefficient, blade loading coefficient, I just give the formula lah. Okay, so flow coefficient is 5, which is CA over U. So you already have the value of CA and U around 0.6. Ya Allah Akbar. CA over U, and blade loading coefficient is CP delta stage just now over U square. Okay, and what else? The mass flow rate. Oh ni panjang sikit lah. Okay, but the method is the same as the exercise previously. To calculate the mass flow rate, you need to first to calculate the velocity C, and then use the ideal gas equation. But first, before that, temperature, after C, velocity, temperature, C, right? And then you calculate temperature, C1, and then you calculate temperature, T1. Okay, the same method as the previous exercise. And then P1 by using the ideal gas equation related T1 to the, this is static, static temperature, don't use the total temperature. So you have to change the total temperature that you have, 1200, to the static temperature. And then pressure by using the ideal gas equation, temperature and pressure. And then, ideal gas, isentropic equation. And then ideal gas equation to get the density, P over rho equals to RT. And then calculate the area. Diameter is given here. And finally, you get the mass flow rate, the same, rho 1, CA, the axial direction of the velocity, CA, and the area. So this is the same previously. And finally, power, the power, saya dah nak habis kelas dah, ada yang nak masuk. Okay, power is the m dot Cp delta T stage, throughout the stage, the difference of the temperature throughout the stage. Dia Cp m dot. So you have 34.6 megawatt finally, the power of the turbine. Okay, power delivered by the turbine. Okay. Okay, so that's it. The exercise for turbine. I'll give you the attendance. Oh, ni. I have to explain a bit about the assignment. Okay. Namanya. Okay, mimbar sekejap Okay, so this is attendance first. Okay, while filling in the attendance, I want to explain about the assignment. So the assignment is accounted for 30%, so it's quite big, the total marks. But you can, you will do in groups, so it's okay. Tab, base learning. Okay, so these are the instructions. This assignment is to be done in groups of 5 students. But I know you guys total 28, so maybe you can do 4, okay, or maximum 4 or 5 per group. Okay, okay. So use the question points raised in the section methodology as guideline to do this assignment. Okay, so basically, this assignment is about the waste heat recovery for a Brighton cycle, which is air breathing engine cycle. So the objective is to create, to design, to propose a design of improve Brighton cycle, which can increase the efficiency. Okay. So give some background introduction, highlight the problems, propose solution, list out all of your friends. So these are the important parts that you have to include in your presentation. Background introduction, of course, the theory part, literature, a bit of the literature review. What is the problem, the current problem of the Brighton cycle, the jet engine cycle exists right now. In terms of propulsion problem, in terms of performance problem. In terms of thrust, in terms of TSFC, the efficiency, okay, focus on that, not on the materials, etc. because this is a propulsion course. Okay, so highlight the problems, the current problems in the Brighton cycle, turbofan jet engine cycle. Okay, and then propose a solution. What can you do in order to improve the cycle, the jet engine cycle, and then list out all your reference that you have. Okay, so I in the last slide I give some of the example. This one, some of the example of the reference. Okay, you can go through this reference. Plus, you can also find your own reference. Okay, other reference, of course. Okay, so for example, like this, an integrated assessment of an organic Rankine cycle concept for use in onboard aircraft power generation. Okay, this one example is that it includes another cycle, which is a Rankine cycle. You have learned about Rankine cycle in thermodynamics. So it is another cycle that we include to the actual jet engine Brighton cycle. Okay, so that this organic Rankine cycle, it is like a power cycle. So it can recover the waste heat from the exhaust nozzle of a jet engine and use it to produce power and for aircraft onboard aircraft power. Okay, so this is example. Basically it is a combined cycle, Brighton cycle plus another cycle. Okay. Yeah, so what you need to do is okay, write a report. Okay, write a report of maximum 10 page, not too long. Okay, just very simple. Just make sure you include all of this, some background study, problems, your methodology, your proposed solution, propose your cycles, and just list out the reference. Okay, and then I want you to present by doing a poster, a suggested A1 size. Okay, and then present in a video about around 4 minutes. Okay, so it's just very simple presentation. You submit the report and submit also the video of your presentation. Just in the video, you just present what is the problem, the current problem that you have found, and what is your proposed solution. Okay. And then so this is some backgrounds. For example, okay, okay, one of the main concepts that are currently under investigation is combined Brighton cycle aero engine. Means that we combine the Brighton cycle engine with another cycle. And then, okay, these are some of the problems to improve performance by heat recovery. Okay, read this one. Okay. So the advantage of the combined gas vapor power cycles, you can have a higher thermal efficiency and produce higher power. Okay, this, for example, some of the problem statements. Okay, so the worldwide consumption of the energy increased to 40%, etc. And however, this energy, not all of this produced energy are used for useful work. Only 12 to 35% of this produced energy are converted to useful work. So there are a lot of energy that are wasted. Okay. So awareness for waste heat recovery, to recover the exhaust waste heat. So the motivation point, okay, in aviation industry is to achieve a better propulsion system performance. Okay, when you read through read all the reference, you might encounter some reference concerning other engines. For example, diesel engine, marine engine, right? Their focus for marine engine or other engine than aircraft is more on the efficiency, on the power consumption, etc. But for aviation industry, we need to consider also the weight added, okay, because you don't want the engine to be too heavy, okay, because you need to fly. And then the most important part is the thrust force produced, thrust power, okay, the power produced, rather than the efficiency. Depends. We still need a moderate efficiency, okay, or moderate propulsive efficiency. But for aviation, Okay, the performance evaluation, the performance parameter which is more important is the how much the thrust force that we can create. Okay. So so this bit of the marking, propose a solution. So in order to propose a solution, you need to do some research, read some literature background, and you have to explain, okay, how maybe you put schematic diagram of the cycle, how the cycle, how the engine, the new proposed cycle works. Okay, for example, maybe you can add some extra heat exchanger to the initial Brayton cycle. You add intercooler or reheat. Okay, so you need to explain the operating principles of the cycles, and then sketch the schematic diagram because you want to understand how the temperature and pressure, the entropy change throughout the cycle, and list of the characteristics of the working fluid used in the cycle and what are its limitations. Okay, this one, for example, if you propose organic Rankine cycle or supercritical carbon dioxide as working fluid for the extra cycle, so you justify, okay, what are the benefits, okay, the advantage of this working fluid, of this fluid. Okay, maybe you use supercritical fluid, so what are the advantage, what are disadvantages, etc. Okay, these are reference. Okay, but you can, it is advisable to search other reference as well. Okay, I think they are more recent reference. Okay, that's all. So I put the deadline 1st July, which is in 2 weeks. Okay, I think the most, maybe just try to submit before, this is before your study week, right? Your study week is 5th July, yeah. 5th July study week, and then 12th July exam week. So at least try to submit by the time study week. Okay? So that you can, after that you can concentrate on the exam. Okay. Okay, I think that's all from me. Later on I will upload all the slides and these instructions of assignment. Okay, if you have any questions, you can PM, WhatsApp or email to me. Okay, as usual. I think 20 students have filled in the attendance. Okay, that's all from me. I don't have any more to say. Okay. Okay, so we stop right now. Okay, we finish our class. If you have any question, you can WhatsApp. Okay, thank you. Tak ada soalan
Thank you, Doktor.
Okay, tak ada soalan. Apa? Digest dulu. Nanti kalau ada soalan tanya. Okay.
Ya, Doktor.
Okay, Assalamualaikum. Stop.
Salam.
Thank you, Doctor.
Okay, stop.
Thank you, Doctor.
Thank you, Doktor.